So we're really glad you could join us. My name is Liz.
And I'm Charlie.
And we are members of the NRICH team based in Cambridge. You may well be joining us as part of the Problem Solving School initiative that NRICH set up just about a year ago now. You're very, very welcome. This webinar this afternoon is taking place as the fourth in a series of 5. And our series of 5 webinars reflect the problem solving skills, the process that we would like students to go through as they're solving a mathematical problem. So starting from that initial point of exploring a mathematical situation and doing something, noticing something, so that would be the first phase. Going in then to some more systematic working, that would be the second. From that point, we hope that students would be able to conjecture and generalise. And then maybe you might think, well, surely that's good enough, isn't it? They've done some generalising. But what we're here today to share with you is the importance of not stopping at the generalising, of asking why. Why have these results come out like this? Why does this pattern always occur? And for that, we're going to think about how useful visualisations and representations can be. So all of those webinars that we've done previously, the 3 we've done previously, you can see recordings of, and we'll point you in the direction of those recordings and the guidance we've already written towards the end of the webinar. But here and now, we're here to discuss visualising and representing. What we're going to aim to do is work on a range of tasks through the session to give you, and therefore we hope your students, a flavour of a range of different representations, which will really stand them in good stead as mathematical problem solvers. Charlie, would you like to kick us off with the first task?
Okay, so just to put a bit of flesh on what Liz has been saying, we might be delighted when students discover that 3 consecutive numbers always add up to a multiple of 3. And then go on to conjecture and convince themselves that 5 consecutive numbers add up to a multiple of 5, 7 consecutive add up to a multiple of 7. Or they may know that to work out the 10th triangle number, you multiply 10 by 11, divide by 2. To work out the 20th triangle number, you multiply 20 by 21 and divide by 2. Or they may know that if you add the first 5 odd numbers, you get 5 squared. The first 6 odd numbers, you get 6 squared. The first 7 odd numbers, you get 7 squared. Or if you take 3 consecutive numbers and you multiply the first and the last, it always gives you 1 less than the square of the middle one. And it's great if they've had that experience of exploring and testing out ideas and finding some results. But like you said, that doesn't seem satisfactory. Mathematicians want to understand why things happen, explain what's going on. And so mental models, images, ways of talking, we've talked about metaphors sometimes being quite helpful, can be helpful. And that's what we're going to be focusing on. Okay, something to start on. Okay, so Liz,
yes.
Maybe we'll use a visualizer.
Yeah, of course.
Are you recording?
I am recording. Okay. Thank you, though, for reminding me, because it is quite crucial. Okay, let's put the visualizer on. Yeah, okay. Right, what would you like me to say?
Okay, so I'm going to ask you to give me, I'm just aware of the way we've written this, so it might be easier for me to write. And I'd like you to give me 4 consecutive numbers. I'm going to ask you to add them together, please.
Right. Do you like me to list them or to only tell you the sum?
No, just choose 4 consecutive numbers.
Okay, 5, 6, 7, 8.
You can tell that we haven't rehearsed this. Is it better to have this landscape or portrait?
Yeah, maybe landscape is better.
Okay, what numbers did you say?
5, 6, 7, 8.
Okay, 5, 6, 7, 8. And what do they add up to?
They add up to 26.
Okay. Okay, so my first request to everybody participating, could you choose 4 consecutive numbers, please? Add them together, and in the chat, can you write down just what your total was? You don't need to tell us what the 4 numbers were. just tell us what the total is, please.
Shall I write out some of these totals, Charlie?
Yes,
That'd be
please.
useful for
Yeah.
10, 46, 50, 22. Oh, they're coming in thick and fast. 30, 48, 18.
I don't think 48 is possible.
Oh, that's interesting.
18. Could 48 be checked, please?
74, 14. Have I said 14? No, 14. 46 we've had, haven't we? Yeah, we've had 46. 54. 90. Thank you very much, those of you who have contributed. Okay.
So, Liz,
Yeah.
what do you notice that all these numbers have in common?
Well, I mean, it leaps out at me that all these numbers are even, certainly.
Okay. So does anybody notice anything else about these numbers? So Liz has noticed that all the numbers that I've got scribbled on my notepad are even numbers. Okay, and Vanessa's noticed that they're all 2 more than a multiple of 4. So they're even numbers, but they're not multiples of 4, which is why I didn't think the 48 was possible. And like you said, we might just stop there. Yeah. But we'd quite like to know why this happened. Absolutely. If we're doing this with students, I think it's important for them to have some way of understanding this. So I'm going to offer an image of why adding 4 consecutive numbers adds up to a multiple, an even number, which is not a multiple of 4. So when we're talking, sorry, there's somebody who's just arrived. Oh, okay. So when we're talking about representations, I suppose the 2 most obvious ones are a visual representation and an algebraic representation. Yeah. And I'd quite like to rehearse what both might look like so that students can see the connections between the two. In the notes, in the guidance notes that accompany this webinar, we have put links to a few articles, and Mike Askew in particular talks about connectionist teachers. Connectionist teachers. You know more about it than I do. Well, you can talk about it while I do a diagram. Thank you very much. Well, I mean the name is in the label. Yes, teachers who make connections between different areas of mathematics. Make the mathematics meaningful for students, deepen their understanding, as opposed to those who convey mathematics as a series of unrelated blobs, I guess. So I'm representing my 4 consecutive numbers as 4 columns, and I'm just assuming that we've got each column is 1 unit larger than the previous one. And I don't really care how long these are. So the first one could be 4, and then the next one would be 5, 6, or 7. But the first one could be 104, which is why I've done the dotted line. Lines are helpful. Yeah. And if I'm going to add them, one thing I could do is I could remove this one at the top and stick it over here. And then all of a sudden, I've got sort of 4 columns here of the same size, but I've got these 2 extra squares there. So the 4 consecutive numbers add up to the total of 4 identical numbers, which will be a multiple of 4, which will also be even, because I can share them out evenly, plus 2. Nice. So I've got something that feels helps to make sense of why this is happening. Absolutely. And I might be able to do this algebraically, but I think I'll wait to do the algebra later. Okay. So what I'd like everybody to have a go at is, can you draw your own your own image, the visual representation of what would happen if we added 6 consecutive numbers.
Mm.
What would that look like? How might you rearrange it? Can you predict what's going to happen when you add 6 consecutive numbers? And then we'll test it out with some examples of 6 consecutive numbers. So we're going to do it the other way around. Instead of starting with the numbers and then trying to explain why,
Okay.
have a go at drawing it and then sort of rejigging it a little bit and seeing what happens. And then in the chat, perhaps you can suggest what's going to be special about all the sums of 6 consecutive numbers.
Brilliant.
Okay.
We'll give you a moment to think about
I'll do the easy bit, which won't give anything away, I think.
that.
6. I'm not going off the page yet.
No, you're doing a good job. You're still on the page. Nice. Okay, we've had a few suggestions in the chat. A few more coming in.
Okay, so there seems to be some agreement, though it's expressed slightly differently.
Well, that's quite nice that it's expressed slightly differently.
Absolutely.
Yeah.
So some people are saying it's 3 more than a multiple of 6, and others are saying it's 3 less than a multiple of 6. And of course, that's the same. So I'm going to try and I'm going to see whether I can figure out what people have been doing. I'm imagining that people might have taken these 3 squares there and stuck them here.
Yeah.
So
you can imagine them rotating around. Yeah.
Go there. And then what we've ended up with is those 3 columns plus most of those 3 columns. And then, so that's 6 identical. If we just take what's underneath the line, we've got 6 identical columns, which is a multiple of 6. And then plus 3, or if we were to think about what's missing, we would get a multiple of 6, but we're missing those 3. So either plus 3 or minus 3 would all work.
Nice.
Okay, fantastic. So, and some people might talk about, oh, you get, because somebody's talked about odd numbers. Yes, you do get odd numbers. So putting all that together, we're getting the multiples of 3, which are not multiples of 6.
Yes.
So we're getting the odd multiples of 3.
Yes.
So we're getting 3 but not 6. We're getting 9 but not 12. We're getting 15 but not 18. We're getting 21 and not 24. And so those would be the results. So we can see why they're odd, because 6 identical numbers will add up to an even number.
That's right.
Plus 2 will give you another even number, and then you've got 1 sticking out.
Yeah.
All right. So I thought we might try 10 consecutive numbers.
Oh, interesting.
But actually, this is an example of where actually the diagrams are taking too much time.
Yeah.
So So being able to do it algebraically makes sense. And let's write down the first one here. If we had a plus 1, a plus 2, a plus 3.
Mm-hmm.
So a plus 1, a plus 2, a plus 3. To describe the 4 consecutive numbers, and we added them all up,
Mm-hmm.
we would get 4 A's,
yep,
plus 6. And why should that make 2 more than a multiple of 4?
Mm-hmm.
Well, one way of thinking about it is, well, that's the same as 4A, which is a multiple of 4, plus 4, which takes you to the next multiple of 4, plus another 2.
Yeah.
So what I quite like, so 4 consecutive numbers gave us multiples of 2, which were not multiples of 4.
Yeah.
6 consecutive numbers gave us multiples of 3, which were not multiples of 6.
Yeah.
10 consecutive numbers, well, I'll let you conjecture what you think you're going to get. Have a go at writing an algebraic expression for 10 consecutive numbers. And see what you get. Can you then interpret it?
Yeah, okay.
So you may get, so when I see 4A plus 6, I know it's going to be even because of 4A tells me, and if I add 6. But I also know that that it's going to be 2 more than a multiple of 4. Have a go at writing 10 consecutive numbers algebraically. And then when you get an algebraic expression, can you interpret it and put something in the chat that tells you what it means? What seems nice in the chat is different people are writing things in slightly different ways.
Yep.
They're perhaps seeing things in a slightly different way. People like Juliet have experience of summing algebraic expressions like this and have then found
choosing.
Started with A minus 4 rather than A.
Yeah.
So so the minus 4, the minus 3, the minus 2, the minus 1 will cancel out with the 1, 2, 3, and 4. Great. So a lot of you are saying, yes. So I think you've ended up with 10A plus 45. And some people have been interpreting this as 10A plus 40 plus 5. So multiple of 10 plus another multiple of 10 means you get another multiple of 10, and then 5 more. Some people have been saying, oh, it's multiples of 5, which are not multiples of 10.
Yep.
Or they've been saying, because I can go from here to 5 as the common factor and 2A plus 9. Some people have been saying, oh, it's the multiples of 5 which are odd,
Yep.
rather than
the even.
Mm-hmm. So what's really nice is that the algebra is speaking to you, and that seems really important. Because you and I have been moaning about our experience at school where we played around with numerical expressions, with algebraic expressions, and they didn't really say anything to us. Yes, a minute ago we were, okay, maybe I'll use it. We were talking about a problem that many of you may know about painted cube, about dropping. So this is a complete aside, but never mind. Okay, so painted cube, you have an n by n cube, and you drop it into a pot of paint, and it comes out, and all the outside is all painted, and then you break it up into all its sort of component parts, all the little cubes.
Individual cubes,
And some cubes have got 3 faces painted, some cubes have 2 faces painted, some cubes have got 1 face painted, and some cubes have got no faces painted. And the 8 cubes that were in the corner will have 3 faces painted. Then the cubes that are along the edges, but are not in the corners, will have 2 faces painted. Now there are 12 edges altogether in a cube, so it'll be 12 lots of, and this we started with an n by n cubed. So we're going to have n along the edge. We're going to take away 2 for the corner pieces. Oops, sorry. So n minus 2. Whereas the cubes that have only got 1 face painted are the ones which are sort of in the middle of each face.
Forming a square.
And there are 6 faces altogether. And they form a square. And each face is n squared, but I need to take away the border, like the frame. So it's going to be n minus 2. And you said it's a square. And inside, imagine like having an onion and you peel the onion. So you take away top and bottom, you take away front and back, you take away left and right, and you're left with a n minus 2 cube.
With no paint.
With no paint. And some students get at this result by seeing what happens if they start with a 3 by 3 by 3 cube, and then 4 by 4 by 4, and 5 by 5 by 5. And they end up with these results, but they don't necessarily, the algebra doesn't speak to them. And in our guidance notes, we've got a link to Dave Hewitt's article called Train Spotter's Paradise, where he complains about just this thing. Students come up with generalizations, but they don't interpret the algebra in the way that everybody has been interpreting the 10a plus 45.
That's right.
So it feels really important that we give the students an experience. And it's lovely because n minus 2 cubed, it's a cube inside that onion. N minus 2 squared, because there are 6 squares on each face, which will provide the cubes with 1 face. And then there's some edges, and then there's some corner pieces. Sorry, that was a ramble. But I think it's well worth reading Dave Hewitt's article, which is in our guidance notes, which accompanies this, and we will give you the link to all that. Okay, so I presume we can predict, can we? If we had 100 consecutive numbers. So with 6 consecutive numbers, we found it was multiple of 3, which is not multiple of 6.
That's right.
With 10, it was multiples of 5, which are not multiple of 10. So chances are 100 consecutive numbers is going to be, am I going to put you on the spot here?
Multiples of 50, which are not multiples of 100.
Right. Now, here's yet another example of where, well, I don't want to do the diagram.
No.
And I don't want to write a plus a plus 1 plus a plus 2 all the way up to a plus 99. So yet again, how can we represent that sum? And And so, you know, Gauss gave us a nice way of thinking about it. So we might do, we've got a problem on the site called slick summing, where we ask students to imagine adding the first 100 consecutive, no, not the first, just 100 consecutive numbers. So we'd have something like that.
Yeah.
And one way of doing this is to then imagine taking that and writing it again, but in the reverse order. So we've got this string of numbers, and we're going to reverse the order. I need to stop banging into that visualizer. Apologies. And
okay, yeah.
And we're going to have an A. And then we're going to add the top of the bottom, and we're going to find that every pair will add to the same total. And then again, that makes sense, because as the terms on the top row increase by 1, the terms in the bottom row decrease by 1.
Yeah.
So we're going to have 2A plus 99, 2A plus 99, 2A plus 99, and we're going to have that 100 times.
Yeah.
And but we only wanted the sum of one string.
Right.
So so instead of 100 lots of that, we're going to have to divide by 2, and we're going to have 50 lots of 2A plus 99.
Nice.
Which means that we've got 50 lots of 2A, which is 100 lots of A.
Yeah.
And 50 lots of 99. Sorry, did I write 55? Yeah. Okay. And why is that going to be 50 more than a multiple of 100? And again, we need our students to, well, you know, just like we did with the earlier examples, we can write that as 100A plus 50 times 98. So I can have, instead of 99 50s, I can have 98 50s.
98 of them, plus another 50.
Plus another 50.
Yeah.
And 50 98 is the same as 49 100. So
yeah.
If I take each pair of 50, it'll make 100.
Yeah.
And I'm going to have 49. If I've got 98 50s, I'm going to have 49 100s. Right. So I've got a multiple of 100 plus another multiple of 100 plus 50.
Nice.
And so we started with something diagrammatic, and then we've got something algebraic. And if we've played around with the 4 consecutive numbers and 6, then we're preparing students for then being able to generalize. And what's lovely about this is then we've got that the power of this is that we can predict what's going to happen with the 100 consecutive numbers, which seems unlikely. It might have seemed unlikely to students at the beginning of a lesson. As they walked into the class,
that's not what they would have expected.
Tell us what you think is going to happen when we add 100 consecutive numbers. The fact that there is something that they have in common, but then, being able to explain it seems to be powerful.
What you did here, Charlie, I guess is a way of, I guess, a different way of represent. It's a sort of another form of representation almost, isn't it? Now you're representing a calculation in a particular way in order for us to make sense of it more easily, I guess. It's a different kind of representation.
I mean, we work with primary school teachers sometimes, and when we're doing this, you often ask me to do a sum, use column addition or something, and because that's not the only way in which we can add, and there are different ways of presenting this. Right. I hope that was useful. But it seemed important to make the connection between the algebra and the diagram. Let's do something completely different.
Okay, good.
We've got a problem on the site called fruity totals. Can we show that?
Yeah, let's show that.
And again, this we will show you. We will give you the link to the guidance page that we've produced. Oh, here's our guidance page.
We're not. Sorry,
it's okay.
The teachers can't see this yet, but I shall go back to it and. Let me share my screen. There we go.
Okay. So we will be sending you a link to this in an email tomorrow or
That's
on
right.
Friday, but we'll also show you where you can find this because it's already on the there's a little introduction here that you might be able to see. Don't worry if you can't read it, but if you scroll down, please, Liz. We've said something about the ethos being, as Liz was saying at the beginning, that we want everyone to understand what's going on. And then we've got lots of examples of problems which can be understood better with visual representations. And the problems we've listed there are sort of in increasing order of difficulty.
Yeah.
So some are more suitable, maybe will be more suitable for primary age students,
yeah.
but and then there are some at the end which are sort of factorizing quadratics and stuff like that with multilink. And what we've tried to do is offer a range so that each one offers a slightly different image.
That's right. That's right.
And then we've got some algebraic ones, and of course there's more similarity between the algebraic ones. But if you go further down, there's this idea that also we use language to make sense of something. And fruity totals, which is linked here, is one of the problems that teachers have said they find really useful for helping students understand and prepare students for working on simultaneous equations.
Yeah.
So here we go. This is what fruity totals looks like. Presumably that's big enough, but I could just, can I do that?
Should be able to, yeah.
Okay, so there are apples, bananas, cherries, and what looks like plums, but they're supposed to be damsons because it's supposed to be A, B, C, and D. But let's call them plums.
Let's call them plums.
And the idea is that they've got some value, and the value is between 1 and 15. And if you add the value of the fourth fruit on each column, it tells you at the bottom what the total is, and on each row what the row is. And what you're trying to find out is what is the value of the apples and the bananas and the cherries and the plums. Let me give you a minute to think about this. Liz hasn't seen this before, so I might give her a minute as well. And I'm not really interested in the value, but have you got, if you want to put in the chat, which rows you look, are there a couple of rows or a row and a column or a couple of columns that you found really useful to hone into? Okay, so somebody's talking about the last, okay, and rows 1 and 3. So the top and left are identical. That's interesting. Somebody said that the column on the right was useful. I can see why.
Yeah.
Because you've got 2 plums and 2 apples, they're up to 26. So that must mean that 1 plum and 1 apple must add up to 13.
Yeah.
And so now if I look at the bottom row, there's 1 apple and 1 plum in it. And they already add up to 13. And so the whole row is 21. If I take the apple and the plum out of that, I'm left with 8. So the 2 bananas are worth 8. And once I know the 2 bananas are worth 8, each banana is 4. And then I suspect the rest is going to be easier because I can go to the top row, the banana's 4. I know that the apple and the plum are 13, so I can work out the cherry. Okay, great. Can somebody, let's look at the chat. Column 4 in conjunction with row 3.
Column 4 in conjunction with row 3. Okay. Okay,
so in column 4, I've got 2 apples and 2 plum apples. In row 3, I've got 2 apples, a plum, and a cherry. And that row is worth 2 more than the far column. So that tells me that cherries are worth 2 more than the plums.
Agreed.
And so that could be, I'm not quite sure how to use it yet, but that is a useful insight.
Exactly. Yeah.
You can represent a cherry in regards to plums. Yes, a cherry's a plum plus two. Good.
Yes. Yes.
Yes. Brilliant. Okay. I think the far right column and the bottom row might have been, I think first and last rows helps. So I think first and last rows. So the first and last rows have got 2 apples and 2 cherries, which we know add up to 26. And the first row and the last row altogether add up to 41. So if I've got 26 already, then I'm missing 15. So the 3 bananas and the cherry are going to add up to 15. And I might be able to do something with that.
Yes.
Okay. Right. I'm not keeping up with all.
I'm not either. But...
Okay. Tell you what, I'm going to show one other one that I prepared. Okay. So here's a different one. Can we have a go at this? And which rows and which columns are helpful here?
Okay.
Actually, this is similar to the one, because I can see that if a lot of people talk about the top row or the second row.
Yeah.
We can work out of 1 banana and 1 apple, and we can use that in the far right column to work out the cherries.
Or the far left column.
Or the far left.
To work out the plums.
Yes.
Yeah.
Okay. Good. Okay, so this is, it seems, a very different way of representing simultaneous equations. But what I like about it is that it encourages quite a playful way of approaching this.
Absolutely.
And what teachers have said to me is, when their students have worked on this, when they went on to do simultaneous equations, they spent much less time having to practice, rehearse standard algorithms, because they were already quite used to doing this.
Yeah.
Okay. I think we should play a game next.
Oh, brilliant. Okay. So we're going to need the visualizer back on. Yeah. Okay.
Okay, so we've got, okay, this is called the up, down, flying around, which we refer to normally as balloon game.
Balloon game.
Because there are 2 balloons, very old-fashioned balloons here. I'm not sure who found the image of this balloon, but anyway. Okay, the reason we're going to introduce you to the balloon game is that a lot of children find it really difficult to understand what's going on when they're adding and subtracting positive and negative numbers.
Yes.
And sometimes children say, 2 minuses make a plus kind of idea.
Yeah.
And they don't have really any understanding of why they're saying that.
Yeah.
So I want to try and convince you that it'd be better to refer to operations by talking about add and subtract, but then when we're talking about what it is that we're adding and subtracting, we're using different terminology. So we're talking about positive numbers and negative numbers. And so we've got a game here. Let me move this here so that you can see Liz's cards. Here we are. And we're going to think about the 4 possibilities. So we can either add something positive, subtract something positive, add something negative, subtract something negative. And the image, the way of representing that I'd like to suggest is that adding something positive is like adding a puff of hot air. It'll make the balloon go up. And likewise, if you reduce the amount of hot air, so if you take away something that's usually positive, the balloon's going to come down. So adding something positive makes the balloon go up. Subtracting something positive makes it go down. Now, sandbags weigh down the balloon. So adding sandbags has a negative effect. So let's think about adding negative numbers, like adding sandbags, whereas subtracting sandbags will make the balloon go up. And so we'll take you take a pair of cards, one from each pile, and you can be the balloon on the right since you're sitting on my right. Do you want to start?
Okay, thank you. So so we've got add, or put that down a bit.
Oh, well, let me just put it here.
Okay, add -4. So I'm adding a sandbag. So I am being dragged down. So I think I'm going to move from 0 to down to -4. What is the aim of the game, Charlie? I presume I've got to fly up into the air.
There is a 20 at the end, and each of us, we're not going to have time to play the, but the idea. Okay, so my turn, and I'm going to subtract -5. So I'm not talking about -5 here. I'm talking about subtracting, taking away -5. Now, when I take away something negative, that makes things better. And we've got an article on the site, and we've linked to it about different models. So we're talking about the hot air balloon model, but Mary, who worked with us in the past, talks about, I don't know, or something positive being chocolate and something negative being detention. And adding chocolate makes you feel positive. Taking a chocolate away has a negative effect, and so on. And there's also a model about buying and selling football players, and you've got really good players. And if you buy a good player, you go up in the league. If you sell your good players, you go down. That kind of idea. So this is not the only model, but it seems important. Okay, subtract -5. I think I'm going to go up 5 places, Liz. So
boo hiss. Come
on then.
Okay. So now I notice here. So now I've got add.
Yes.
Add +3. So I'm getting puffs of hot air. I think I'm going to go upwards. 1, 2, 3. I'm on -1. You're still beating me.
And you're not saying ++3. No. You're talking about adding and subtracting. So we've got a mixture here of cards. Sometimes they've got the plus or the minus sign, and sometimes we've got the word. And here the next one, add +5.
Oh dear.
So I think we're going to have to stop now because we're going to run out of time.
Funny that we've stopped when you're.
But it's a good place to stop. Good.
But this is a great example of where actually our use of language is key in helping students understand the mathematics, what's going on, I think, isn't it? It's really lovely.
Yes. So I was going to mention very quickly tree diagrams. Shall we stop sharing?
Yeah.
Of course, there are many other visual representations. There's one problem on the list there that uses a graphical representation. Talks about the charge at a car park when you arrive and how much for each hour. And you have 2 different car parks. and which one is it better to go to. And in one, they charge a lot to start with, but very little for the extra hours. And in the other one, a little bit to start with, but more for the extra hours. And representing that graphically makes it really clear which car park to go to if you're only going to be staying for 2 hours, and which car park to go to if you're going to stay for 10 hours, and where the dividing line is. So being able to represent things graphically, being able to present things algebraically, having good models is really important. Tree diagrams is another example. When we're doing probability, we have sample space diagrams, tree diagrams. So I sometimes get students to picture what they would draw when they're flipping a coin. And let's imagine the top one is going head and the bottom goes tail. And then we can think, okay, well, what happens if I flip 2 coins and I can go, okay, head, 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 tail, tail, head, tail, tail. And this helps us make sure that we don't miss any combinations. And then I get them sometimes to draw, and they work in pairs, and one person's got the drawing and the other one person has to try and picture, can they do head, head, for 3 coins, head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. You can see I've been practicing.
You're showing off now.
But you want students to be able to, in the way that we did slick summing, you didn't need to do all the bits in between because you can picture it. We were reading Jo Bowler's work, and she talks about how important it is to use many more visual images, encourage us to do stuff in our head if we can, and that what we write reflects what we're seeing and reflects how we're thinking about the situation.
Absolutely.
Okay, I'll stop. We should show where things are on the site.
Let's go back to the website and just point you in the direction of not only the guidance we've written today for today's webinar, but also the previous webinars and the previous guidance as well. So here's Fuji Totals. If we go up to the Problem Solving Schools menu, I'll choose the top level menu. This takes us to our main Problem Solving Schools page, and on the right hand side, this box, the Resources and Development Professional Development page. Here you will find all the guidance and the recordings of webinars we've created so far. Those processes of working through a problem, the mathematical thinking skills you can see on the left hand side. Thanks, Charlie. So we start off with exploring and noticing, working systematically, conjecturing and generalizing, and then today's focus, visualizing and representing. So those the resources on the left-hand column will take you to a guidance page. So we're offering some thoughts on how you can best support your students to develop those aspects of mathematical thinking. And in the previous 3, you'll find already recordings of our webinars. And on the Visualising and Representing page, we've got the primary webinar recording, which was we had the webinar yesterday, and very soon we'll have today's recording as well. And Charlie's already taken you through this page a little bit, but you can see that we have linked to all the tasks we've been talking about today that we've worked with you are linked here with a short description of why we've included them, why they offer particularly useful representations for you to have a look at with your students. We hope that what we've done today has been useful, and that you'll be able to support your students in working mathematically, and particularly in visualizing and representing. Just to alert you, our 5th webinar in the series, I believe, is going to be on January the 22nd.
Yes, the secondary teachers.
The secondary teachers. That'll be reasoning, convincing, and proving. So we do hope you'll join us then. We do have another webinar before that, which is on the 20th of November, which is focusing on maths beyond the classroom, and that's for all teachers. One webinar. So we hope to see you there as well. Finally, did you have anything else to say, Charlie? About
I want us to remember to mention Trinity College, who...
Thank you very much. Well done.
There is a feedback form.
There is a feedback form, yes. Trinity College very kindly fund these webinars so that they are free for you to participate in. So we do appreciate that very much. And I'm trying to copy a link to the evaluation form, and I'll pop that in the chat now. If you could give us your feedback, we'd be very appreciative. It really helps us to consider how to do better next time. You may need to unfortunately copy the link and then paste it into your browser. I know we had a little bit of trouble with that yesterday, so apologies if that's the case. Thank you again. Thank you, Charlie.
Yes. Sorry, I feel I ought to say something and I don't know what to say. When this finishes, we'll think of things that we forgot to say.
Of course.
We have included problems about visualizing and representing organized by year group.
Yes, you're absolutely right. Yeah.
Which might also be very helpful to everybody.
That's right. If we go back to the page, the left-hand column represents the guidance and the recording of the webinars, but here on the right-hand side, you also have links to a whole range of secondary problems, which will particularly lend themselves to students focusing on representation.
And somebody has asked about the webinar dates.
Yes, of course.
So I'm going to go to the teachers page. I'm going to scroll down to events. And here we've got today's event, and then future events are all listed here. So on the 20th of November, as Liz was saying, we're going to be doing some work on Maths Beyond the Classroom. For those of you who are part of the Problem Solving Schools initiative, there are some statements in the charter which are about maths beyond the classroom. So that's particularly interesting. That should be of particular interest for those of you who are working, trying to develop that area of what you offer your students. And then the 22nd of January will be finishing this set of 5, which will be focusing on reasoning, convincing, and proving. But there are also dates for webinars in March, May, and June. Quite shortly, we will be posting on this page the details for registering.
Yeah, further details and links, so you can.
So that was, go to teachers and click down on events, and that takes you to the events page. Go to problem solving, resources and professional development, take you to the webinars and the guidance page.
That's right.
Right.
Thank you. Thank you all very much. Have a good rest of the day, and we hope to see you at a future event. Thank you.